Okay, so in this video, what we're going to do is quickly summarize qualitatively the gas laws. In other words, we're not going to do the calculations. The calculations we'll do on separate videos for each gas law. But this one, I just want to use this simulation here to go ahead and give us an idea of how these gas laws work and what the relationship is between the variables within the gas laws. We've got volume, temperature, and pressure that we've got that are going to be variables that can be changed on a gas, and we're going to see how all that goes ahead and works. So I'm going to go ahead and bring up my PowerPoint. Okay, and the PowerPoint is right here. I'm going to talk about the three original empirical gas laws: Boyle's law, Charles' law, Gay-Lussac's law, and then we'll talk about the combined gas law, which is it's called the combined gas law because it's a combination of these three laws, and we'll see why that is. Real quickly here, in chapter 13, they talked about the kinetic theory of gases, and I'm just going to go through these real quickly just to kind of give us an idea of what gases are like, what they behave like. Okay, so the first bullet point says a gas is composed of particles, usually molecules or atoms. These particles are considered small, hard spheres that have insignificant volume and are relatively far apart from each other. Between them is empty space. We can see it here when I bring this up. Now, these gas particles are supposed to be much smaller, much bigger than the actual gas particles would be. So you can see them, right? So each of these gas particles, each of these bouncing spheres right here, is supposed to be a gas particle. But in real life, they would be incredibly much smaller, so you can't see them. But we're making them big enough so you can see them. Right? Each one of them is moving randomly, and they're basically going about their business. There is much more space in between them than there is, than the size. So the size of the volume of the container is much bigger than the volume that they take up. If we added the total volume of all these gas particles, it would just fill up just a tiny little portion, a little corner of this container. And if the gas particles were actually their actual size, it would take a teeny tiny bit. So the volume of the container is usually much larger than the volume of the gas particles. Actually, the total volume of the gas particles is considered insignificant. So, between them is empty space. There are no attractive or repulsive forces between the particles. In other words, they don't stick or they don't repel each other. The particles in gas move rapidly in constant random motion. They travel independently and they travel in straight lines until they hit another particle or another object. And once again, we see that here. They're all going in a straight line until they hit something. So we're following this one. Got hit, hits the wall, hits another particle. They're going in straight lines until they hit the wall or until they hit something else. Okay. And all collisions are perfectly elastic. This means that collisions occur without loss of kinetic energy. In other words, they don't stick to each other, but they just bounce off of each other. An inelastic collision would be one where they stick to each other, like a ball in a mitt in baseball. These are just more like billiard balls. They kind of bounce off of each other. Okay. So that's basically the kinetic theory of gases, just explaining how gas particles behave in a gas. What you would see, if you could see gas particles, what you would see. Next slide is on variables that describe a gas. We talked about pressure in chapter 13. Letter P is going to stand for pressure, and it's the force per unit area exerted by the gas particles. Really, it's the number of the number and the magnitude of collisions against the walls of the container. So as you can see right now, a lot of these particles are hitting the walls of the container, some of them harder than others. So the gas pressure would be a indicator of the average the average collision and how hard it is. The harder they're hitting, or the more often they're hitting, the higher the pressure. The lighter they're hitting, the slower they're moving, or the less often they hit, the lower the pressure. Second one is volume. Capital letter V will be used for volume, the amount of space that the container that the gas particles are in. The third is temperature. capital T, lowercase t is used for time. So capital T is temperature, and it's a measurement of the kinetic energy of the gas particles. And moles, we learned about moles in chapter 11. We're going to use lowercase n to represent moles. Um, and it's how we measure how many gas particles. The more gas particles, the more collisions, and therefore the higher pressure. The less gas particles, the less collisions, and the lower pressure. Okay. So we're going to look at our laws and how these variables are related to each other in those laws. The first one is Boyle's law. Boyle's law basically says that pressure and volume are inversely proportional to each other. What that means is that as the volume decreases, like we're showing here we're going to start off with some initial volume. We'll call this V1. We're going to use these subscripts for these gas laws. There's going to be ones and twos. And the ones mean at the first point in time, twos mean the second point in time. Okay, so you have a volume to begin with. Then you change that volume by pushing something in, and you'll get a new volume. And so here we see a larger volume to begin with. We call that V1. And then we could push this in here and make a second volume with less space. We call that V2. We can measure that. And basically what Boyle's law is saying is that as volume decreases, and this says right here, if volume decreases, pressure increases. Because the same number of particles are supposed to be in here, as long as you have the same number of particles happening. And this, by the way, is happening at constant temperature. We don't change the temperature. And we'll talk about why temperature is important in the next gas law. But if our temperature stays the same, all we did was make the volume smaller by pushing in the piston on this gas chamber here. And then we made a smaller volume. Now the particles are going to start they're going to start bouncing against each other more often and against the walls of the container more often. We can see this if we go back over here. Okay. So I have a specific pressure, a specific temperature. Here's my temperature, 300 Kelvin. Pressure, 7.3 atmospheres or so, about 7 atmospheres or so. And we got a specific volume I'm sure we can measure if we wanted to. Just measure length times width times height. I'm going to go ahead and hold temperature constant, so it's not going to change. And what I'm going to do is, you'll notice that you can kind of count. Well, let's actually see this. I'm going to count how many collisions in a certain sample period. And this thing says, oh, if I wait 10, apparently these are 10 picoseconds. There was 46 collisions with the wall of the container. If I run another sample here, there's going to be 42. So 46, 42, they vary from sample to sample, but you can get an average, right? They're roughly around 40, 41, 38 in this next sample period. So roughly about 40, right? Well, 36 is a little bit lower. And if you get an average, you'll end up here, the one's 46. They're roughly around 40 right now. If I go ahead and I make this volume smaller, notice that there's less space, so they're bouncing against each other more often. The temperature is held constant. Remember that temperature is a measure of the kinetic energy. In other words, the average velocity of the particles moving. Higher the temperature, faster the particles will be moving. But since our temperature is constant right now, they're all going the same speed. But because you have less space, notice our pressure went up. And the reason the pressure went up was because now I'm going to go ahead and click on the collisions. And you'll notice that if I take a sample, let's see, there was 51 in that sample period. If I do another one, 52. So notice that last time they was averaging roughly about 40, 41, 42. Now they're in the mid 50s. Why? Because the volume is smaller, there's less space, so the particles are hitting against the wall more often, and that's what increases the pressure, right? The pressure before was about 7 atmospheres, now it's about 11 atmospheres. So our volume got smaller. Is that the smallest I can get it? I guess it's the smallest I can get it. Our volume got smaller, and the pressure went up. So that's what it means to be inversely proportional. We can show it here in a graph. Right? As the volume gets bigger, the pressure gets smaller. As the volume gets smaller, the pressure gets bigger. Okay, and that's an inverse proportion you see in Boyle's law. And we have an equation for Boyle's law that we're going to go ahead and come up with, and we're going to use it. But right now, I just want to show you the quantitative relationships. Okay. All right. So that is Boyle's law. Let's move on to the second one. On another video, I'll go ahead and do a sample problem using Boyle's law. Okay. Charles' law is the next one. And Charles' law, basically what it tells you is if you increase the temperature, it'll increase the volume, assuming the pressure is constant. So in Charles' law, Boyle's law, we kept the temperature constant. We didn't change the temperature. And we saw the relationship between pressure and volume. In Charles' law, we're going to keep the pressure constant. And we're going to see what happens as you change the temperature, what happens to the volume. Basically, the idea is if you heat it, volume will increase. And much the same way, if you cool it, the volume will decrease on its own. So, okay, so we're going to see kind of a demonstration here of Charles and Gay-Lussac's law. It shows you the relationship between temperature and volume. As temperature increases, volume increases. Here they're showing you as the temperature goes up, our volume goes up. And that's because as temperature goes higher, the molecules move faster. It's not showing it here, but molecules move faster against the same pressure, a constant pressure. So as temperature goes up, molecules moving faster, and they push around. I think it looks better over here. So here we have some gas particles in a container, and it's got a certain volume, and this volume has a piston which is allowed to move. We're going to keep the pressure the same, and what we're going to do is we're going to increase the temperature. So you're going to see an increase here in the thermometer and see what happens as you increase the temperature by heating it up, putting a flame underneath it, then see what happens to the volume. Okay. So as you can see, temperature is going up, and so is the volume. Okay. So that's kind of showing you that the higher the temperature, the higher the volume. Okay, we can watch that again. As the temperature goes up, the volume goes up too. This one doesn't have it, doesn't show it, but the volume, if the temperature decreased, so does the volume. I will show a demonstration what happens when you decrease the temperature. You'll also decrease the volume in just a little bit. Unfortunately, our other gas properties one, this one did not have a way that you can change the volume automatically. Like in a cylinder here, this volume is kind of set. So I had to go ahead and find another one. But that's Charles' law. As volume goes up, as temperature goes up, so does volume. As temperature goes down, so does volume. Um, and so we have this here. You can plot it, and when you plot it on a graph, you get something that looks like this. Now, every different gas, depending on the nature of the gas, and depending on the on the um, on the amount of gas, gave a different line, each with a different slope. The curious thing is that they all met at the same place. So whenever anybody took a sample of a gas, um, and they had a different gas, they'd get a different line with a different slope. But they'd all meet right here about 273 degrees below 0 Celsius. Now, some of you guys may recognize that number as the coldest it can be, actually. So what they did is they decided, you know what? Let's convert our Celsius temperatures. Let's make a new scale called the Kelvin, and we'd go ahead and subtract all the Celsius temperatures. Let's subtract 273 from them, and we'll put them on what we call the Kelvin scale. And what they found was that when you did that, all the all the lines met at 0. Okay, so every gas, depending on the type of gas it is and the amount, has a different line, but they all meet at 0. And the relationship is, as you increase the temperature, you increase the volume. So they are directly proportional. Okay, so later on, we're going to see how we can use that to calculate Charles' law. The third gas law we're going to talk about is, in a similar way, it is Gay-Lussac's law. And Gay-Lussac's law is when you hold the volume constant, volume is held constant, um, the, the Kelvin temperature is proportional to the pressure. Once again, this only works if you use this new Kelvin temperature scale that we've been using. And I can go ahead and show that again here. This one I can show on this. So we're going to hold our volume constant. And here the pressure is roughly about 5 atmospheres. If I heat it up, then what happens is the temperature starts going up. Let's say I had to go up to 338, get up to 438. Now the pressure has gone all the way up to 11 atmospheres. So as the temperature went up, the particles are moving faster. And since they're moving faster, the pressure is higher. If I cool it down, let's try to cool it down to, let's say, 100 Kelvin. Notice that the particles are moving slower. This is what happens when you cool, so now let's say 138. When you cool down a gas, particles move more slowly, they don't bounce against the walls of the container as often, and the pressure drops. Right? So heat and temperature increases, so does the pressure, right? Temperature is going up over here, pressure goes up. If I cool it, temperature goes down, gas particles moving more slowly, and the pressure drops. Okay, so we will be coming back to this and using what we call Gay-Lussac's law for when we have temperature and pressure changes. And there will be sample problems in a little bit. Okay, the last gas law that we're going to be talking about is the combined gas law. And the combined gas law is when nothing is held constant. So each of the other gas laws, in Boyle's law, we kept the temperature constant. In Charles' law, we kept the pressure constant. And in Gay-Lussac's law, we kept the volume constant. This one, nothing is constant. What do you do when nothing is constant? Well, you end up with another law that relates the pressure to the volume to the temperature. Okay. So here's your summary, and these are going to be the equations that we will use: Boyle's law, Charles' law, Gay-Lussac's law, and the combined gas law. And I'll talk about each one of those and do a sample problem with each one of them.